In this video, I'm going to look at transformation of functions and their graphs. So we're going to look at, say, starting with a function such as y equals x squared, and then multiplying and adding different constants at various points to the function to end up with a new function. And look at how those constants impact the graph as they're being added to the function of y equals x squared. But before we start, I want to look at something we've already done, which is when we did transformation with geometric figures, because I think there is a good correlation between how the two behave. So imagine this situation where I have a shape of a geometric shape such as an arrow, and I am going to first do a translation. So we have a translation down by a certain number of units, and then a reflection, and then a rotation. So the order was translate, reflect, rotate. Now let's see what happens if I change the order of those three transformations, but keep the sizes the same. So the orange is where we ended up at. I'm now going to start with a rotation, followed by a reflection, and then a translation. So we have now gone rotate, reflect, translate. So exactly the opposite steps, but we've ended up at the same point. Let's try that again, but this time I'm going to start with a reflect, then a rotate, then a translate. And again, you see that we end up at exactly the same point. So the order does not matter as long as the magnitude of the rotation, reflection, and translation stays the same. So now let's look at functions and their graphs. You can see that we have this generic function and the various transformations that can occur to that function, where we have a constant being multiplied by the function and then various transformations inside and then a plus constant at the end. So here's an example where we have 3 outside of f, 2x plus 1, and then plus 5. You can see that these two are not quite the same because here a is taken out as a factor of x plus b, while the example given, the 2 isn't a factor outside of x plus 1, the 2 is just a factor of the first term. Before we start, the first thing we need to do is perform that factorization. So I am going to factorize this to make sure the format is the same. And then, just like where we were doing the transformation with geometric figures, we can identify specifically the purpose of the half, the 2, the 5, and the 3. We're going to start with our standard quadratic function fx equals x squared, and we're going to look at the impact of each of those constants. I'm first going to look at the function when only there are transformations horizontally. So I have an a being factorized outside x plus b, and anything that happens inside the function results in horizontal transformation. So I'm going to select my red function. You can see they're the same because my variables, my b is set to 0, my a is set to 1, so that ends up being f of x. My c and k are irrelevant in this function. What we want to identify is to see if it matters if we do the horizontal translation first, then dilation, or the other way around. So let's do a horizontal translation, and let's do a horizontal translation of 1 unit. So my b is 1. It results in a translation to the left of 1 unit. And then I am going to change my a to 2. So b1, a2 results in a translation to the left and a horizontal dilation of factor 1/2. So I first applied my horizontal translation, then my dilation. Let's take a mental image of where we're at. We've got our x-intercept at -1 and y-intercept at 4. Now let's do this the other way. So I'm going to do my dilation first and my translation second. And you can see that we end up at exactly the same spot. Now let's look at the y transformations. So I am going to turn my black curve off. And I'm going to first do my vertical translation. Let's go up by 2. And then do my vertical dilation. And let's set vertical dilation to 3. So you can see our turning point is at 0, 2, and we have a point at 1, 5. Now, let's do that the other way, where we apply our dilation first and then our translation. And again, you can see that we end up at the same spot. So let's put all of that together, turn this graph off and go back to the combination of all. So that's my green graph. Now, if I do my horizontal first, let's try to match 2 outside of x plus 1/2. So my b value is 1/2. You can see our turning point is at x equals -1/2. Then we apply our horizontal dilation. So now I have changed the graph by a factor of 1/2 horizontally. Then let's do our vertical translation, and it was +5, so I need to go to 5. And we have a vertical dilation of 3. I'm just going to move this graph. So we have a y-intercept at 8, our stationary point at x equals -1/2, y equals 5. Now I am just going to change the order of moving these levers. So let's do our k first, 3. Let's do our a next, which was a 2. Our b was 1/2, our c was 5. You can see we end up at the same place. So the order, just like with transformation of geometric figures, is not relevant. I could do this first, I could do my k second, I could add my 5 next, and I could then perform my dilation, horizontal dilation. I end up at the same point. The order is not relevant. What is significant is making sure we get these values correctly. We get the format in the form of k, f, a outside of x plus b, plus c sitting at the end. Notice k is not a factor of c. If you get that correct, then it doesn't matter what the order is.